All right, everybody. So what we're going to be looking at today is the method of substitution. And yeah, let's get right into it. So we know that every derivative formula is an antiderivative formula. So we know every derivative formula is also an antiderivative formula if you just kind of flip it around. So specifically what we want to do is we want to look at the chain rule. The chain rule, which is a derivative formula for derivatives here, says, what does it say? So the chain rule says this: if you take the derivative with respect to x of a function that's in a function, you get the derivative of the outside function times the derivative of the inside function. Now, as an antiderivative formula, what's that look like? Well, we'll show you, right? So as an antiderivative formula, it says the integral of f prime g prime x dx. So of course we're just integrating the left-hand side. That is going to be simply f of g of x plus c. Okay, and yeah, so that's what it says. Now, unfortunately, this is not quite how we do what I'm actually going to call substitution, because it's not easy to recognize this happening. So we want to use this to help us do integrals. Use this to help us solve problems, right? Help us solve integrals that we're given. But it's hard to recognize. So it's hard to recognize a f prime g prime x in a problem. So you don't do it directly. You don't just look at it and see the left-hand side and then write out the right-hand side, because that's not really just how people's brains work. What you do instead, when you start with an integral like this, f of g of x, f prime g of x, g prime of x dx, like this, what you're going to do is you're going to try to figure out what the inside function is. Actually, you know what? I don't want to write steps yet. We'll just do that for an example. So I'll just write it out here, and then we'll look at it. So the idea here is this: there is an inside function called g, and so what you're going to do is you're going to say, let u equal g of x. I realize that this is what I just erased pretty much. All right. So you say let u equal g of x. But then if you take the derivative of that, then you would have, not that, you would have du dx. So you take a derivative, and you get du dx equals g prime of x. Now what you're going to do on all of these, and so what I just wrote, you generally won't even write. What you're generally going to do is you're going to take this dx and actually use algebra and just move it over to the other side here, up next to that g prime. So you're going to generally write du equals g prime of x dx. Okay? And the reason you want to do that is because if you look at your integral, there is a g prime of x, just like there is highlighted in green down here. So what you're able to do is you make a substitution. So if you substitute those two things, u equals g of x and du equals g prime of x dx into your integral, right? So your du is going to get replaced, sorry, your g prime of x dx is going to be replaced by du, and your g of x is going to be replaced by u. So you just come up to the integral and say, well, what's that going to say? It's going to be the integral of f prime g, but we just wrote that g is u. And then g prime of x dx, but g prime of x dx is du. So you make the integral look like what I just wrote. Well, now that looks like a much simpler integral. So now it's so simple, it looks simple enough to solve. So you do solve it. So we're looking for, in this case, an antiderivative of f prime u, but the antiderivative of f prime would just be f. So you would just have f of u plus c. Now you're not going to be able to leave your answer like that, however, because the variable u was one that I made up to solve the problem. So you always have a last step where you're going to replace the u back with what x was. So they would call that like back substitution or something. Substitute back to the original variable. Right? What was the substitution? It was u equals g of x, right? So you just put that back in, and it's going to say f of g of x plus c. All right? And that's really not doing anything different than what we already wrote, right? Because I started with this integral here, and then I ended with this answer right here. And that is actually just, together, that's just this formula. So all I did was work through that antiderivative formula just in a much longer way. Okay. Now the reason I did that, though, is because that much longer way is actually how you perform integration by substitution. Those are the steps. Okay. So let's actually solve indefinite integrals now with substitution. Let us try to do that. So we're not going to start with one that's super easy. We're just going to start with the normal one, okay? This is just straight off of the homework here. So they want us to find the antiderivative. And then what's the antiderivative? It is negative 7 x to the 3 parentheses 6x to the 4 plus 1 to the 6th dx. Now I'm going to rewrite that before I do anything. I'm just going to take that negative 7 out. It'll be easier for me to show you something if I do that. So I will do that. All right, so I'm actually going to look at it that way, with the negative 7 out of the integral. Okay. Now, in order to do substitution, well, first of all, you need to notice that you can't just do this integral, right? So notice that you don't know the antiderivative. It's not on your list of common functions, right? It's not just power rule. Power rule only works for powers of x, not powers of x multiplied by other stuff. So notice that you can't just write an antiderivative. You don't know one, okay? So we'll try substitution, because it's the only advanced technique we know. In Calculus 2, you're going to come up with a big list of methods for solving integrals, and we don't have any yet, so we can't do that. All right, so what's your first step? Your first step is that you are going to figure out the u. Try to figure out the u. The u. Now, what's the u? It's generally going to just be a function that was inside of another function. Inside of another function most of the time. Not always, but most of the time that's the case. Now, the reason that's going to be the case is because if you think about the formula here, right? The u is the g, which is inside of the f prime here. So you do want to look for a function in a function. So when I look at this integral right here, I see this is a function in a function, right? So you need to identify that and notice it, and that's what you're going to make your u. So once you decide on the u, you say, I want not that color. You say, let u equal whatever you decide the inside function is. Now, if you get it wrong, then this is going to go bad for us somewhere along the way. But no, we didn't get it wrong. We got it right. So we try to figure out the u. It's generally a function inside another function. So we got it right. Now, what are you going to do with that? Well, we're just following the steps up here, really. So after you have that, you're going to take the derivative. Now, it's best if you can go from here, straight from here, just because it's one less line of work. So yeah, but take the derivative. So I will take 2 lines of work this time, but in the future, I'm not going to keep doing it this way. So we're going to take our derivative, which is going to be du dx is equal to, I'm taking the derivative now. So this is a derivative, a regular derivative. So the derivative of 6x to the 4th is 24x cubed. And then the derivative of 1 is just nothing. So I just get 24x cubed. Okay. Now, what you're almost always going to do is you're going to rearrange this here. You can either just solve it for dx, or you can solve it for something that you see in your problem. And let me look at the problem real quick. Yeah, okay. So you kind of do have a choice here. I'm going to write this as a separate step, but normally I would just do it as part of the taking the derivative step. You want to solve that du part of the equation. Solve the derivative part. Either for dx or for something that you see in your problem. And I know that that's vague. But let me just write the problem down real quick. So the problem as I have it right now is -7 integral, and I'm going to rearrange this already. I'm going to write it parentheses 6x to the 4 plus 1, right? That's what I have right here, to the 6th. And then I have an x cubed and a dx. So I'm going to put the x cubed and the dx right there. Okay, and so my idea is that I see an x cubed and a dx. And over here in my du, I have an x cubed and I have a dx, right? So instead of solving just for the dx, which I said you could do and it works fine, I'm going to solve this for x cubed dx. So I'm just going to rearrange a little bit. So I just go du is going to be 24x cubed dx. I realize that I have an x cubed dx right here, but I don't have a 24, right? There's no 24 here. No 24. So I will take the 24 and move it over to the other side and have du over 24 is x cubed dx. Okay, so that's what I mean when I say solve it for something that's in your problem. X cubed dx is in my problem. So I've got the x cubed dx, which matches perfectly with the x cubed dx. And I also, up here, I have a 6x to the 4 plus 1, which matches perfectly with the 6x to the 4 plus 1. So once you have that kind of thing going on, you make your substitution now. Make substitution. Now, after you make your substitution, all of your x's should be gone and only u's should be left. Should be gone, like, or cancel. And only u and du should be left. If that doesn't happen, your substitution was wrong. So let me rewrite my integral here. So my integral is -7 integral, parentheses, 6x to the 4 plus 1 to the 6th x cubed dx. And of course, the point is that this right here is simply u, and this right here is simply du actually over 24. So you make that substitution, and my integral becomes -7 integral, this is u to the 6th du over 24, which I could write this way. I could take the 24 out because it's just a fraction. -7 over 24, it's just a constant multiple, and then just have u to the 6th du. So that's what I get after I make my substitution. And the point is, after I do that, after I make my substitution the way I just did, that I should have, hopefully, an integral I know how to solve. So I should be able to now solve the integral. All right, let's try it. So I have -7 over 24, integral u to the 6th du. What's the antiderivative? Well, this is just power rule now. So the antiderivative of u to the 6th is u to the 7th over 7 plus c, which I can see that my 7's cancel, and I'm just going to get -1 over 24 looks like u to the 7th plus c. So I did my integral. But now my last step is actually you have to replace the u with what it was in terms of x's. So you have to substitute back to the original variable. All right, and let's do that. So we have -1 over 24, u to the 6th, sorry, u to the 7th, but u, come on, highlight, u is what we have here, 6x to the 4th plus 1. U is 6x to the 4 plus 1. So you just replace it, 6x to the 4 plus 1 to the 7th plus c. And that is your answer. Okay. So that was an entire substitution integral. Now I realized that we just took up a lot of space to do that, but a lot of my space was stuff that didn't necessarily need to be done. I was just writing it to help you out. All right, let's try a different one. But that was very typical. That one was very typical. All right, not ready for that yet. Next one, come on. No, come on. Okay, here we go. This one's gonna blow your mind. That was a joke, it's not. All right, so here's an integral. Negative 2 x squared x to the 3 plus 6 to the 4 dx. All right. Now my only concession this time to working this integral, I'll take the 2 out. I didn't really need 2. And then I could write it as x to the 3 plus 6 to the 4, and then x squared dx like that. So I'm just moving where I write that, x squared. And that's because I know that's going to be part of the du momentarily. All right, so let's try to do this. So here's what I think we do. Number 1, let u equal what? Hopefully you know now it's the inside function. So what I just highlighted. So u is x to the 3 plus 6. Okay, now you're going to take a derivative. So the derivative is du dx is 3x squared. How did I get a 24 up here, by the way? Oh, because it was 6x to the 4th. All right. Du dx is 3x squared. Now, I don't leave it that way. So typically what I'm going to do is I'm going to actually write it just as du equals 3x squared dx. And that's how I normally would have started. Now, I can see x squared dx in my problem here, x squared dx. So I'm going to choose to divide the 3 over to the other side and have du over 3 equals x squared dx. All right. Okay, good. So once we have that, I should actually be able to do my substitution now. Right? I've got this. U is x cubed plus 6. X squared dx is du over 3. So that just means we should be able to come over here and say, well, this is u. This is du over 3. So you just make those substitutions now. So let's see here. I've got negative 2 integral u to the 4 and then times du over 3. So we need to integrate this. So take the 3 out with the 2. So it's really just the integral of u to the 4th du, which we know how to integrate. The integral of u to the 4th is u to the 5 over 5 plus c, so we're integrating here. So we got negative 2 over 15, u to the 5 plus c. But then your last step, you have to back substitute, or substitute back. Back substitute. So I have negative 2 over 15 u, but what's u? U is x cubed plus 6. To the 5th plus c. And there you go. That is one whole substitution integral. All right, and you see we did it in a lot less space, but there are a lot of steps. And so you have to, I don't know, practice this and you'll get better at it with practice. I'm going to try to find one that looks a little bit different. You have a whole bunch of ones that look exactly like the two that I did, And when I say exactly, I mean like exactly. They just change a couple numbers. Just looking for one that's a little bit different. I don't know if I'm going to see it, so I think I'm just going to... oh, there we go. Here's one. As soon as I say I don't know if I'm going to see it, we see it. But we'll do one that's a little bit different now. Negative 17. Sine to the fourth. T. Oh, they make it a T. All right, so we have this one. Now, there's nothing different about this. The only thing is that you have to remember, first of all, I can take that 17 out. That's not what you have to remember. What you have to remember is that when you see something like this, when you see something like this, that a sine to the fourth that way is really a sine t to the fourth like that. Okay, so you don't want that notation that they're using to confuse you. So you want to write it like this before you start, because then you can identify the inside function easier. So we're going to try substitution. So we're looking for, let u be the inside function. That's what generally you're looking for. So u is going to be what? How about just the sine t? Not sine to the fourth, just the sine t. So just sine t. All right. Then what do? We got to do a derivative, right? So I'm going to skip that step that I've been doing. Instead of writing du dt, I'm just going to write du. And then you take the derivative of sine t. The derivative of sine t is cosine t. And then I'm just going to put the dt right there on the end. Okay? I mean, that you could have done that in 2 steps. So that's what we have. Now what we need to do, so there's no step 3 this time, so the numbers are going to be different than the previous problem. I don't even have any solving to do right here. I've got this cosine t dt, which I can see is already right here. So we're already ready to substitute in. So my integral is going to be the integral of negative 17 integral sine t to the fourth, but sine t is u, so that's u to the fourth. And then cosine t dt, right? But this is all just du. This was a u. So this is just du, no du over 3 or anything. So that's my integral. Look at that, pretty easy. So now we need to integrate it. Integrate. So I've got negative 17 integral u to the fourth du. That's going to be another power rule. So the power rule for u to the fourth is u to the fifth over 5 plus c. Last step, we're going to substitute back to x, well, t. So we get, looks like negative 17 over 5, and then u to the fifth, but u is sine t. So sine t plus c. And that is your answer. All right. Okay. Now, another way you could have this is, in this case, we had the trig function inside of the power function. That's not always the case. You could also have that reversed, where you have a power function inside of a trig function. So here's one. 2t to the 3 cosine t to the fourth dt like this. Now again, we should be getting better at this. So what do we want to do? We want to decide on the u. The u is the inside function. You should be able to look at this and realize that this should be your u. So let u be t to the fourth. Right? We're going to do a derivative. So du is 4t to the 3 dt. I'm going to solve that for, I'm going to rearrange that really, is all I'm going to do. I'll say rearrange. So what I notice, I didn't rewrite my integral, but I've got a t cubed and a dt. And here I have a t cubed and a dt. So all I need to do is move that 4 over and have du over 4 is going to be t cubed dt. So then my integral, so let's see here, sub in, substitute. So my integral, which was the integral, I'm going to take the 2 out, cosine t to the fourth, I'm going to write the t to the 3 dt over here. I've got a u right there, and I've got a du over 4 right there. So my integral is 2 integral cosine u du over 4. Okay, so now we integrate. So I'm going to get 2. Okay, so actually 2 over 4, I should say. What's the antiderivative of cosine u? You need to know that, right? Sine u. And then finally, we need to substitute back in. So I'm going to substitute back in. I'm going to have 1/2 sine u. I don't know why I made that so big. What's u? U is t to the fourth, right? U is t to the fourth. So t to the fourth. Done. All right. So I think at this point you should have a pretty good understanding of what substitution looks like. What we haven't done yet is substitution when you have limits of integration. So way back here at the top I said solve indefinite integrals with substitution, and then we did. Well, now we need to solve definite integrals with substitution. All right. So, good news. Very little changes. All right. In fact, if you want nothing to change, then you can make it so nothing changes. I'll show you an example. So this is the way I don't recommend, but I'm going to say you could do it this way. So not the recommended way. Example. Okay, so this is not how I recommend to do it, but you can. All right, so let's say you're doing an integral from 0 to 1, and let's say it's, I don't want to make it too hard here, so let's just say x squared plus 1 to the 3 x dx. Okay, so there's my integral, and this looks a lot like the ones we've already done substitution on. You could just basically, your first step is do substitution completely like normal all the way to the end. Just keep those limits of integration. Keep the limits. Okay, so I'm going to do this quickly because I don't recommend this as the way to do it. but you got an inside function, right? So u is x squared plus 1. So du is 2x dx. So du divided by 2 is x dx. So at this point, I've got a substitution for u, and I've got a substitution for du over 2. So my integral becomes the integral from 0 to 1 of, looks like, what is it, u to the 3, and then du over 2, which is, I can take the 1/2 out, integral from 0 to 1 of u cubed du. Now here's a warning though. The warning is this. The limits of integration here are not in terms of u, they're in terms of x. So you can't plug those into x, or sorry, into u. So the limits are for x, not u. Okay, so that's just, I'm just pointing that out right now. So continue on with this integral. We have 1/2. The integral of u to the 3 is u to the 4 over 4 from 0 to 1, right? Because it's a definite integral, so we have to evaluate it between the limits f of b minus f of a. Now again, before you substitute those limits in though, you need to substitute back to x's. Right here, before you plug in numbers. So you have to go 1/2, wait, yeah, that's right, but I'm going to take out as 8. The 4 and the 2 in the denominator there. So u to the 4th, u is x squared plus 1 to the 4th, 0 to 1. And then now that I'm done, I can do my, basically, I'm calling it step 2 now. Now you plug in your limits. Do f of b minus f of a, right? For a definite integral. So we get 1/8, put in a 1, 1 squared plus 1 to the 4th. I don't know why I have square brackets. 1/8, 1 squared plus 1 to the 4th, minus 1/8 0 squared plus 1 to the 4th. So this is 2 to the 4th, which is 16 over 8, which is 2, minus 1 to the 4th, which is 1 over 8, which is a half. So I think it's 3/2. All right, and we're done. All right. So that works. Like what we just did, that's a perfectly acceptable way of performing definite integration. However, the other way expects us to change the limits, and it can save us work in specific types of problems. So I will show you how. It won't really save too much work on the problems that we have to solve, but we'll try it. I need to go back to the beginning of the assignment here. Substitution. Hey, I know how to do that. And so do you. All right. All right. So the recommended way is going to be when you do your substitution, you come up with new limits for the u. That lets you skip the step where you go back to x's. So where you go back to the original variable. Now, if you hate this, then don't do it. But this is how I would do it. All right, let's try one. And there's no real way to do it other than just doing one. So let's do it. -1 to 0, it says. X to the 3, parentheses, 4x to the 4, minus 2 to the 4th, dx. Ugh. All right, here we go. Here's my integral. So we're going to start out doing this like normal. So everything's normal here. So we're going to let u be the inside function, which by now you should be able to pick out pretty easily. There it is. So du looks like 16x to the 3, right? dx. And I know that I have a x to the 3 dx and an x to the 3 dx. So just the 16 is going over to the other side. And I have this. Okay, great. Now, I'm going to make my substitution now. So substitute in, sub in. So I am going to write my integral here. So my integral is, I'm going to write this, x equals -1, x equals 0. Just to make it clear, those were for x, right? The original variable. Now my integral, this right here is u to the 4th. So u to the 4th and then the x cubed dx is du over 16. So I've got this integral here, 1 over 16 integral -1 to 0 of u to the 4th du. But the whole problem, not problem, but the issue with this is that the integral is u, but the limits are x, right? Integral is u. The limits are x. So what I'm going to do that's different this time is I'm going to change the limits to be in terms of u. All right, so it's not hard at all, but you need to be okay at algebra to try it. So the idea is this. We have, what's the substitution, right? The substitution is u equals 4x to the 4th minus 2, isn't it? We have that. So that's the u. So what you do is you just plug the limits of integration in for x. What are the limits of integration? They are -1 and 0. X equals -1, x equals 0. Okay, so this is what I normally would write. I would normally write, I go like this. I go top limit. What's the top limit? 0. So the top limit is 0. So I go, the top limit is x equals 0. That implies, well, if x is 0, I'm just going to take that and plug that in for the x here. So I've got 4, 0 to the 4th minus 2. What's the result? Minus 2. Actually, let me rewrite this because I did a dumb thing here. So x is 0, and then u is 4, 0 squared. Sorry, 0 to the 4th. Minus 2. Which you work that out, and it's minus 2. And so this is your new top limit. Right? U equals -2. New top limit. Now what about your bottom limit? You do the same thing. So the old bottom limit was -1, right? Yeah. So you plug that into your substitution for u. So you have u equals 4, -1 to the 4th minus 2. So you work that out, you get 4 minus 2, which is 2, and then that's your new bottom limit. Okay? So my integral is actually, come on. So my integral now is actually this integral. It was 1 over 16 integral, and it was -1 to 0. Now it is 2 to -2. Really? Okay. 2 to -2, and then just u to the 4 du. And the thing about this is that the limits are in terms of u, so you never have to go back to x's now. So that's what this work helped you with. So now solve the integral. So I solve the integral, I get 1 over 16 antiderivative. The antiderivative of u to the 4th is u to the 5th over 5 from 2 to -2. And I can use these limits for u, right? That was the whole point. So I can just write 1/16 u to the 5 over 5 minus u to the 5 over 5. I don't know why I put the 1/16 on the outside like that. That's not how I have been writing these, but this is fine. So you work that out, and you get, looks like 1/16 -32 over 5 minus 32 over 5, which is going to be 1/16 -64 over 5. And then, -64 over 16 is 4. Is it? Yeah. So -4 over 5. It's good to use a calculator that does fractions and then not have to do it in your head. Okay. So that's the recommended way. So the recommended way is to change the limits over the way that I just did. Okay. And they do that if you look at the book. So, or Newton will do it with my recommended way. Not everybody does it, it's just kind of what makes you happy. I'm looking for one with trig. I'll just make one up if I don't see one quick enough. So you can do this with any definite integral, and there's nothing like remarkable about it. It's just, do you want to change the limits or do you not want to change the limits? And either one of those is fine. Way to do it. All right, come on, one more. Next one's going to be trig. Yeah. Okay. Last problem, guys. Example. Integral. Nope. Why would I even say negative? It's not negative. 7 pi over 6 to 2 pi of -8 cosine x sine squared x dx. Right? Now I'm going to be a little bit faster with the substitution than I have been here. So u is going to be sine x, not sine squared. Du is going to be cosine x dx. Right? So the idea is, the sine x is your u, the squared is on the outside. And then you have cosine x dx. So I go to make the substitution, pretty quickly I can get my substitution is going to be 7 pi over 6. I'm leaving it that way for now. Those are x's. I have my -8 on the outside. Sine squared x is u squared. And then cosine x dx is du. So this much is just a regular substitution so far. But then I'm going to change the limits. So change the limits. Not litmus, limitus. Limits. So remember, u is sine x, right? It's right here, right here. So my old top limit is x equals 2 pi, right? So my new top limit is going to be u is sine of 2 pi. So just grab a calculator or something, or Wolfram Alpha. Sine 2 pi is 0. All right, that's my new top limit. Now for my bottom limit, I have, what was the old bottom limit? It was x equals 7 pi over 6. So my new bottom limit is going to be u equals sine 7 pi over 6. Now, like, you can use a unit circle or a calculator. I'm using a calculator, hand calculator that happens to do this symbolically. So I'm just doing sine 7 pi, 7 pi over 6. It's negative 1/2. It should be, oh no, because I'm in degree mode. I mean, it should be 7 pi over 6, right? I mean, 1/2, negative 1/2. All right. So you do those, and so my limit or my integral becomes, so the integral is now negative 8 integral from negative 1/2 to 0 of u squared du. So you see how we got rid of all the complicated stuff out of here? There's no pi's, there's no trig functions, nothing. So that's why you like to do this. So I'm going to keep going. So I have negative 8. I need an antiderivative, u cubed over 3 from negative 1/2 to 0, which I'll take the 3 out. Negative 8 thirds, u to the 3 from negative 1/2 to 0. So that's negative 8 thirds, put in a 0, minus negative 8 thirds, put in a negative 1/2. See what we get. Looks like this first one's going to be 0. Then I have a minus, which is a plus 8 thirds. And then negative 1/2 to the 3 is negative 1/8. 8 thirds times negative 1/8. The eighth is going to cancel. I think I get negative 1/3. Let me see if I do. I do. So there you go. All right. So I hope you kind of see what the advantage is of changing your limits to be in terms of the new variable. It lets you avoid the step of going back to the x's, only for definite integrals. Okay. So that is that. I think this is going to be the end of the homework that you have due, so that's good. Let's stop here.